It's Flashcards Fridays, and today, 3 flashcards look at 3 scientists whose work fundamentally changed their fields. They worked in different disciplines, lived in different eras, and faced different obstacles. What connects them is not symbolism or representation. What connects them is that their differences expanded what science was able to see and solve. But before I begin, a quick word from my advertisers. Scientific progress rarely arrives because a community agrees. It arrives because someone notices a detail others ignore, approaches a problem from an unfamiliar angle, or insists on following evidence even when it's inconvenient. History shows that many of the breakthroughs that reshaped medicine, chemistry, and environmental science came from people whose perspectives were not considered standard at that time. In the early 1980s, AIDS was a medical crisis without a clear cause. Patients were arriving with collapsed immune systems, rare infections, and no unifying explanation. Theories circulated widely, but evidence lagged behind speculation. Political hesitation slowed the research, and many laboratories were reluctant to associate themselves too closely with a stigmatized disease. Flossie Wong-Staal approached the problem from a molecular perspective. Trained as a molecular biologist after immigrating to the United States from China via Hong Kong, she specialized in understanding how viruses behave at the genetic level. Her expertise focused on how viral genetic material integrates into host DNA and how that integration produces disease. At the National Institutes of Health, Wong-Staal became a central figure in efforts to identify the cause of AIDS. She helped clone and sequence the genome of HIV, demonstrating that it was a retrovirus and explaining how its structure accounted for the progressive destruction of the immune system. This work required sustained technical precision rather than dramatic experimentation. It depended on methods that were still developing and on confidence that molecular evidence could cut through social, political, and medical uncertainty. While many researchers focused on symptoms or behavioral explanations, Wong-Staal focused on mechanisms. That focus changed the course of the epidemic. Once HIV was definitively identified as the cause of AIDS, blood screening became possible, transmission pathways became clearer, and antiretroviral drug development could begin. Millions of lives ultimately depended on that molecular clarity. Wong-Staal's contribution illustrates how scientific progress can stall when problems are approached from too narrow a set of perspectives. Her training and intellectual orientation allowed her to see structure where others saw chaos. And Wong-Staal's work shows how progress can depend on someone who is willing to narrow their focus when everyone else is still arguing broadly. Once a scientific field accepts that kind of precision, a second question emerges. What happens when we stop treating knowledge as something we merely discover and start treating it as something we can deliberately build? That shift from explanation to design marks a different kind of scientific leap, one that requires comfort with abstraction, structure, and long-term thinking. Chemistry often advances not through discovery alone, but through redefinition of what counts as a solvable problem. Omar Yaghi's work exemplifies this shift. Born into a Palestinian refugee family, Yaghi pursued chemistry with an unusual emphasis on structure, symmetry, and design. Rather than treating materials as substances to be found in nature, he approached them as architectures that could be deliberately constructed. Just last year, in 2025, he was awarded the 2025 Nobel Prize in Chemistry, shared with Richard Robson and Susumu Kitagawa. His unique way of thinking led him to found the field of reticular chemistry, which focuses on building materials from molecular components assembled into predictable, repeating frameworks. His most influential creations, metal organic frameworks known as MOFs, are porous materials capable of storing, separating, and capturing gases with extraordinary efficiency. These materials have applications ranging from carbon capture and clean energy storage to water purification and chemical separation. What made them possible was not just technical skill, but a conceptual shift. Yaghi treated chemistry as a design science rather than a catalog of existing compounds. That shift expanded the field's imagination. It allowed chemists to ask not only what materials exist, but what materials could exist if molecular assembly were treated as an engineering problem. The result was a new class of materials with global implications. Yaghi's work demonstrates how science benefits when practitioners bring unconventional frameworks to familiar problems. His background did not merely add diversity of identity. It contributed diversity of method. Yaghi's work reframed chemistry as a discipline of intentional construction, but it also revealed a second truth about scientific progress. Creating new possibilities is only half the task. The other half is recognizing unintended consequences once those possibilities are released into the world. That responsibility requires scientists who are willing to follow chemical logic beyond laboratories and into ecosystems, even when the conclusions disrupt economic or political comfort. In the 1970s, chlorofluorocarbons were widely regarded as safe and useful chemicals. They were stable, non-toxic at ground level, and commonly used in refrigeration, aerosols, and industrial applications. Few questioned their long-term environmental impact. However, Mario Molina did. Trained as a chemist and working in the United States after growing up in Mexico, Molina studied atmospheric chemistry at a time when the upper atmosphere was poorly understood. Along with his colleague, Sherwood Rowland, he investigated what happened to chlorofluorocarbons once they escaped into the atmosphere. Molina's work showed that these stable compounds eventually reached the stratosphere, where ultraviolet radiation broke them apart. The resulting chemical reactions destroyed ozone molecules, thinning the ozone layer that protects life on Earth from harmful radiation. The conclusion was scientifically sound and politically unwelcome. Chlorofluorocarbons were economically important, and early warnings were met with skepticism and resistance. Molina persisted, continuing to refine the evidence until the chemistry became undeniable. His work led directly to global policy action. The Montreal Protocol, signed in 1987, phased out ozone-depleting substances and is widely regarded as one of the most successful international environmental agreements in history. The ozone layer is now slowly recovering. Molina's contribution illustrates how scientific insight often comes from asking questions that fall outside institutional comfort zones. Molina's perspective allowed him to connect industrial chemistry with atmospheric consequences in a way that had not been widely considered. Taken together, these three stories point toward a shared dynamic that transcends field or era. Breakthroughs tend to arrive when science widens its interpretive lens, not when it narrows it. Each of these scientists advanced knowledge by refusing to stay confined within the dominant assumptions of their time, and each demonstrated that progress depends as much on who is allowed to question as on what is already believed. These three scientists did not advance their fields by conforming to expectations. They advanced science by expanding its range of vision. Each brought a way of thinking that was initially peripheral and made it central through evidence, persistence, and results. But most importantly, they advanced science because the academic institutions embraced diversity and encouraged these brilliant individuals to keep studying, keep researching, and keep experimenting. Their differences were not incidental. They shaped how problems were framed, which methods were trusted, and which questions were pursued. When institutions allowed those differences to operate rather than suppressing them, progress followed. This is what diversity does when it functions well. It increases the number of viable approaches to complex problems. So, what are our three takeaways? Well, first, scientific breakthroughs often depend on representation, because representation is how science gains access to the full range of human knowledge, training, and lived experience. When institutions narrow who is allowed to participate as an expert, they do not protect standards, they discard insight and weaken their own capacity to solve complex problems. Second, diversity accelerates scientific advancement because it increases the number of viable approaches to a problem. When researchers from different countries, disciplines, and lived experiences work on the same question, errors are identified faster, assumptions are challenged earlier, and solutions emerge more quickly and more robustly. Third, history shows that societies advance faster and more reliably when institutions resist discrimination and expand participation. The most effective solutions emerge when people from different countries, cultures, and intellectual traditions are empowered to contribute, and when evidence is allowed to outweigh comfort, hierarchy, and familiarity. The history of science leaves little room for ambiguity. Discrimination is not a neutral social flaw that science somehow rises above. It is a structural barrier that slows discovery, distorts evidence, and delays solutions that the world can't afford to wait for. When institutions restrict who belongs, they restrict what can be known. When they commit to representation and inclusion, science becomes more accurate, more resilient, and more capable of meeting reality as it is. Diversity is not an optional value layered onto discovery after the fact. It is a necessary condition for progress itself, and history shows that when science is narrowed by discrimination, everyone pays the cost in lost knowledge, lost time, and lost lives. The present moment is where these costs are either accepted or challenged. The present moment is the time to seize responsibility while it is still possible. With that said, carpe diem, my friends.